Welcome back to another episode of Chemistry. We're going to talk about how to calculate energy using a concept called specific heat capacity. Specifically, we're going to talk about how specific heat capacity is related to energy and energy when it comes to combustion, and then applying the formula to do with specific heat capacity, and then we're going to do some practice questions. Now, the thing with energy is it's not something that we can see. Say, for example, you go and fill up your car with petrol, and the petrol provides the energy source for the car to run, right? But it's not like you can look at a bottle of petrol or whatever's coming out and go, I reckon that petrol's going to have this much energy. It's not like you can't stick your finger in it and go, oh, definitely 100 joules of energy. So we can't actually measure it directly like that, right? But what we can do is, we see how much work you can get out of it, and through that value imply how much energy has come out of your fuel source. So a way we do that is we use the fuel, we make it heat something up. In other words, we make it do some work. Now, specifically for us, because we're in a lab and we're talking about chemistry, we're probably going to heat up some water. And then once we do that, we measure any changes. So in the case of heating the water, we measure the temperature change and go, it's changed by 5 degrees. Now that change can be attributed to a certain amount of energy that was input into the water to make that change occur. So whatever we calculate from that temperature change, the energy released to allow that temperature change to occur, we say, well, all of that energy came from the fuel, and therefore the fuel has this much energy. All right, there's a lot of words, so let's kind of keep moving. So when it comes to the lab and you're doing it in the classroom, this is a very typical setup for us to actually do these calculations, energy changes, to figure out energies that come from fuels. So what you'll generally have is you'll have a fuel here, and it might be ethanol, it might be methanol, I don't know. It's whatever fuel is safe to use in your lab that your teacher actually has access to. Now, what it will generally come in is what's called a spirit burner. So this is like a bottle. So think of it like a candle. So you put the fuel in there, you light it up here, and what will happen is the fuel will continue to drive the actual burning of the fire. And then what you'll do is just above it, you'll have the substance that you want to heat. Now, a lot of the time, as I've mentioned before, that's probably going to be water. So you might have some water, a water sample in here. You're going to try and heat it up. And during that experiment, you're going to use a thermometer to measure the temperature change. No duh. What it might look like something else in the lab is you put your beaker here, got it on top of a stand, or depending on how you want to make it, there's your spirit burner again here, the spirit burner. Then what's going to happen is it's the fire, that will then heat up the water that's in there. And again, you've got a thermometer to measure the temperature change, and that's really important. I've spoken a lot about the concept of specific heat capacity. So the question is, what does that actually mean? Now, specific heat capacity is, and it's represented by this symbol here, C, how much energy is required to raise 1 gram of the substance by 1 degree. For example, the specific heat capacity of water is 4.18 joules per gram per degree. What that means is it takes 4.18 joules to increase the temperature of 1 gram of water by 1 degree. Now, you don't have to remember that number, but you'll get so used to that number that it'll just come automatically. If you forget, in your in your data book, they actually have the value here. So either in the units of kilojoules per kilogram per Kelvin, or joules per gram per Kelvin, or you can use degrees Celsius. And the reason why you can get away with using the degrees Celsius is it's just temperature change. Whether it's 1 degree Celsius or 1 degree Kelvin, it's the same thing. Now, just be careful. Most of the time, we like to use it in that units. So joules per gram per Kelvin. But if you decide that you want to use it in kilojoules, make sure that the other unit in terms of the mass is in kilograms. So don't mix them up. Cool? All right. So how do we apply specific heat capacity to actually calculate energy change? This is the formula I need you to know. And that is the energy that's released from a fuel when you're using it will depend on the mass of the substance that you heat, the specific heat capacity of that substance. So say, for example, you're heating 100 grams of water. You're going to use the 100 grams of the water that you're heating. This capacity is going to be the specific heat capacity for water, so the 4.18 joules per gram per degree Celsius. And the delta T means the temperature change. Now, please, 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 when it comes to the mass in this formula, it's the mass of the substance that you heat. It's not the fuel. So never use the value of the fuel in this equation. It's the value of the substance that you're heating. I see this mistake happen way too much, and it's a very easy mistake to make because these values will be in your question. Again, if you forget, you're not really expected to memorize this formula. However, it's really handy if you do because it will just come as second nature. In your data book, again, you can see the formula matches there. Q, so energy, MC, delta T. Now, let's do a worked example. So say you're going to use 0.3 grams of methanol. And what you're going to do is you're going to heat 100 grams of water, and what has happened there is that there's been a temperature change from 20.1 degrees to 37 degrees. Now, if you're someone who likes to visualize it and draw it out, so if we've got a spirit burner down here, there's your fire, there's your methanol down here. I'm just going to write, actually no, I won't write methanol down there. Now that's 0.3 grams of that. Now, and then what you have on top, and of course it's not floating, so you probably have some sort of tripod or something like that. Now water, you've got 100 grams of water in here that's being heated. And the water has been heated from 20.1 to 37 degrees. What we have to do is we go, if this is the results from this particular setup, what's the energy released from the methanol? So we're going to go to that formula, MC delta T. Now the mass, see how you've got two masses to choose from? Either it's the mass from the methanol, which is actually your fuel, or it's the mass of the 100 grams of water that you can heat. You choose the substance that you're heating. So that means we're going to use 100 grams here. The specific heat capacity of water we know is 4.18. Oh, this is horrendous. Sorry about that. And the temperature change is whatever 37 minus 20.1 is. Okay, so whatever that is. So do your calculations there. So the answer you should get is just over 7,000 joules. Now remember, when you're using this formula, with the units that you've got, the units of the answer of the energy is going to be in joules. So that's 7,064.2 joules. So how does that help us calculate the energy of fuel, or the enthalpy of a fuel? Now, what you can do is you figure out, well, how much energy was released in the experiment. So in our previous question, 0.3 grams of methanol, when you use all of that, it was able to release just over 7,000 joules. How do you know that? Because that was the energy that allowed the water to go from 20.1 degrees to 37 degrees. Once you've got that value, then you can actually figure out how much energy is released in kilojoules per mole. So let's do a follow-up to that worked example. Again, same scenario, but this time we're going to calculate the heat of combustion, right? In delta H, and it's probably, let's just say we're going to go for kilojoules per mole. So when you've got this, really you need two pieces of information. You need how much energy, and you need how much in terms of the number of mole that you've used. In other words, we need two pieces of information. We need the energy, and we need the number of mole. Now, if you ever get confused and you forget about that, one, it's in your data book. Two, look at the units, kilojoules per mole. This is energy, this is mole in N. Now, the energy we figured out in the last question, 7064.2. That was joules. Now, notice how we need it in kilojoules. We're probably going to need to convert that into kilojoules, right, before we do the calculation. So instead of that, we're actually going to use this value instead. So let's just draw an arrow. Oh, God, this pen is horrendous. So that's how many kilojoules. Now, we need to figure out the number of mole, right? Now, the value that we have is 0.3 grams of methanol. We need to use that value and then convert that into mole first. So if you do that calculation, you know that in the 0.3 grams of the methanol, divide it by 32, which is the molar mass, and you should get a value of 0.009375 mole. That's how many mole of the fuel that you used. So that's actually the value that I use in this calculation. So I'm going to put this value right here. Excuse the horrendous numbers. Right, so once you do that calculation, you should get about 753.5 kilojoules per singular mole. Cool? So you can see how you do that. As you can see, I've run out of space, so I haven't put it to the right sig figs, but according to this, the right number of significant figures should be only 2. So that should be probably about 7.5 times 10 to the 2 kilojoules per mole. Let's do another question. Another question. What if I used instead 0.4 grams of ethanol, use the whole 0.4 grams, to heat up 150 grams of water, and it goes from 25 degrees to 50 degrees. Now what we have to do is calculate the delta H, right? The delta H in terms of kilojoules per mole. Let's say that's the units that they want it. Now again, if that's the case, my goal here is to be able to get, so to figure out the delta H, so I need two variables. I need the energy that was released in this reaction, right, in heating up that water. Then I also need the number of mole of ethanol that I actually used. Before I can even use this formula here, which is my final goal, I need two other pieces of information. So that's where we're going to go first. Let's calculate the energy first, right? So let's put a thing on the side. Let's calculate energy. Now, you know that the energy, also known as, actually, I should probably put Q instead of E, hey? That really means it's the energy that was released from the fuel to heat up the water. This is when the MC delta T thing comes into play. So you can see here, MC delta T is the mass of the water. So the 150, the specific heat capacity of water is 4.18, and the delta T is really 25 degrees, so whatever the difference between 50 and 25 is. The value that you should get is just over 15,000 joules, which we know we're going to need in kilojoules, so I might as well do the conversion now. 15.675 kilojoules. So now I've got the energy value. The next thing I want to do is I want to find the value of the mole. So the mole of the fuel, which is my ethanol. So 0.4 grams of ethanol, the molar mass of ethanol is 46. Should be just over, 0.00870 mole. Cool. Now I've got both of these values. I've got the energy released and I've also got the amount of the fuel used. So now I can actually use this original formula, which is, so putting those two values into here, you can see the 15 kilojoules on top of the number of mole that's used, which is this value here. So we should get roughly around 1,803 kilojoules per mole as the delta H for ethanol. So to summarize, what we can do is we can actually use the energy that was released during combustion and absorbed by a substance to actually calculate the enthalpy of a substance. How do we do that? We can use this formula, Q equals MC delta T, that relates to the specific heat capacity, to figure out how much energy was released, how much energy was absorbed, and attribute that to the fuel that was being used. Cool? All right. And always, no matter what anybody says, yeah, you can.